Go ahead and introduce myself and we'll start recording. Good evening, everyone.
By the way, Janet, can I interrupt your introduction? I see Adam Durant is online. I just see a comment in the Q&A. I did my MS and PhD with Raymond, Will, and Bill. It was an amazing experience collaborating across Geo and Atmos. Yeah, so Adam, shout out to him. Adam's an alum, obviously, who has been very successful and I believe is the mastermind or maybe even CEO of a really creative company in the UK that takes satellite imagery and uses it for the aviation industry to help them avoid dangerous things in the atmosphere like volcanic clouds. So Satavia, I think, or Satavia it's called. Anyway, cool.
Nice to meet you indirectly, Adam, and thanks for joining us. Yeah. All right. So good evening, everyone. My name is Janet Callahan. I'm Dean of the College of Engineering. This is our last Husky Bite of the season of 2020, in fact, and we have two special guests this evening. We have co-host Will Cantrell, who I'll be introducing in a moment. And then our featured speaker this evening is Ray Shaw. These are both professors in the Department of Physics. And so Will be introducing Ray in just a moment, but it is my pleasure to introduce Will right now. So Will, Dr. Cantrell was recently appointed as Dean of the Graduate School and Associate Provost, I believe I have that title correct, here at Michigan Technological University. His area is a similar area to Ray, as we were just discussing in the remarks leading up to this. Will has a BA in physics that then led to a PhD earned in atmospheric science at Alaska Fairbanks, where we were just discussing the coincidence of his PhD mentor being Dr. Ray Shaw's father, which is you know, and that's why I was like, Ray, did your dad make you do a PhD in atmospheric science? So Will joined Michigan Tech in 2001. After having done a postdoc in the Department of Chemistry at Indiana. Was that Indiana University?
Yes.
Hey, that's where I spent my freshman year, by the way. And then, and so he's had a distinguished career at Michigan Tech. And I want to tell you two fun facts about Will. He likes to fly fish and cross-country ski. And this is the season for cross-country skiing, not fly fishing. So with that, Will, I'm going to turn it over to you to introduce Ray, and so welcome everyone. I always forget to do the opening slides. I actually should do them right now, so I'm going to very quickly share screen so that I do this because we have a very important. Can you see my screen?
Not yet.
All right, give me one moment. Share screen. Desktop. All right, now I've lost my slides. Hang on. All right, here we go. So opening slides. So we have been having a series of these this fall, and this, as I mentioned, this is our last one. I would really like to sincerely acknowledge the sponsorship of Michael and class of 69 and Karen Gregory, as well as I want to kind of re-acknowledge Amy Otis Lang and Walt sponsorship from a previous webinar. These are all posted and live streamed. I do encourage you to look them up if you missed one. And I did want to briefly launch this poll, Ray, so you could have an idea of who was joining us tonight. And so Sue, if you could cue that up, please, I would appreciate it. So we have an audience that's very diverse. We have, you know, a whole bunch of students ranging from graduate students to undergraduate students to prospective students through alumni, faculty and staff, curious people. It's all over the place. And so already this evening, we have 131 people here. And we can see that about 60% of our attendees are alumni. We've got about 12% Michigan Tech students. So welcome Michigan Tech students, it's nice to see you. We have 7% curious people, 5% family of current or future students, and then we have a big group of Michigan Tech faculty and staff. All right, so that's your audience, Ray. I just wanted you to know that. And I wanted to, let's see. All right, so I'm going to stop sharing and so Ray, you can start sharing and we'll go ahead, please, and introduce Dr. Shaw.
Thank you, Janet. It's my pleasure to introduce tonight's speaker, Dr. Raymond Shaw. He is distinguished professor in physics. But let's go back a little bit. As we've established already, I think Raymond grew up in Fairbanks, Alaska. From Fairbanks, he has a bachelor's degree in physics from Brigham Young University, went to Penn State for a PhD. From there, became an advanced, was a member of the advanced study program at the National Center for Atmospheric Research, which is a very prestigious and competitive postdoctoral fellowship, and then joined the Department of Physics in 1999 here. As a faculty member here, Raymond has worked on a variety of subjects. I'll just mention two. I think he's going to talk a little bit about the cloud chamber tonight, and one of the things that led into that was his interest in turbulence. So the reason why you see the chaotic motion behind him is because the motion in the motion of the air in the atmosphere is never just one direction. It's always jumbled up. And so that's one of the things that Raymond has studied. One of the other things that intersects directly with the background is how water freezes. And I won't spoil the punchline because I know that Raymond is going to talk a little bit about this, but I will say that you have the privilege of seeing two people who have more practical experience with ice nucleation. So this is something that both Raymond and I have studied, and we know, a great, most of the people in the field who do this kind of work, but I think most of them don't have the practical experience that we have, because I know that both of us have moved tons of snow off of our roofs and off of our driveways. And I don't think there are other people in the field who can say they have that level of practical experience. And with that, I'll turn it over to Raymond.
Okay, thanks, Will and Janet. I really appreciate the invitation to be here. And there's a Q&A. Please go ahead. Anybody out there listening in, post your questions. I think we'll have an opportunity at the end, and we'll do our best to answer as many as possible. So those of you who have lived in the Keweenaw know exactly what this title means, and you've experienced it in a very personal way if you've lived here for at least a winter. Sometimes it really does feel like a good chunk of Lake Superior is in your driveway. And like Will said, we gain a lot of direct hands-on experience with moving snow. It's kind of a big production up here. In fact, as we were discussing earlier, I grew up in Fairbanks, Alaska. And I remember when I came to interview at the job here, people were warning me about the winters. And of course, I was internally rolling my eyes and thinking, what can the Upper Peninsula of Michigan possibly have on Fairbanks, Alaska? And it is true that, in terms of temperature and darkness, it's nothing. But I never could have imagined. I mean, I remember the first winter living here just thinking, it's still snowing, and it's still snowing, and it's still snowing. So it was actually quite impressive. So I'm going to start out kind of general and give you an overview, show some nice pictures and things like that. And then I'm going to share a few tips and tricks for forecasting lake effect snow. So if you want to be able to, let a little bit of your nerdiness show and learn ways to impress your friends and tell them, oh yeah, I think there's going to be a band of intense lake effect snow come through. I'll share some of that with you. And then towards the end, I'll get a little more advanced and show you a little bit of the research that we're doing here at Michigan Tech to study different aspects of lake effect snow, things that maybe could make your lake effect snow forecast a little bit better in the future. So first of all, let me just There we go. I'm going to say thank you first to a whole long line of grad students who have worked on various ice and snow related projects with me. There are others who have worked with Will. And in fact, you see Adam's name here. We talked about Adam, got a chat comment from him earlier. Let's see, current student Elise Roski, you'll see a video that Elise put together a little bit later in the presentation. And I also want to do a shout out to Matt Zika from the National Weather Service Marquette office. In fact, there are several people from the staff there that have had a really great relationship with Michigan Tech. They come, they help us teach sort of an informal forecasting course that we do with the students here. And it's really great to get there because they're really, you know, the ones who know the system better than anybody else. They're looking at the weather here every single day, especially during the winter. So I want to.
So Elise is here. Elise Roski is here this evening.
Awesome.
And I was trying to write these down so I can tell you who else is here, but if you are one of those people here, send a quick note in the Q&A and just say, hi, I'm here.
That'd be great. So here are some photos. These, I mean, you can look on the web and find millions of these, of course, from the UP. These happen to be all of various members of my family. This over here on the right is me clearing part of Lake Superior out of my driveway, in fact. We talked about shoveling your roof. That's a real thing. This might not even be the first time. Sometimes we've had to shovel our roof 2 or 3 times during the winter, which is kind of depressing sometimes. These were my kids when I first moved here. And this was doing a little service at the church that I go to. So we had to clear out the fire escape exit or something like that. I mean, you can see it's kind of an intimidating amount of snow. And this is my daughter who discovered that it's much easier to clear your driveway. This was after a big storm. I was conveniently out of town, and she and my wife sent this picture. So she was doing it in layers here. So she would shovel the top layer and then go down to the next layer. So very methodical there. So we have some questions for tonight. And to get us started, this one's not a right or wrong answer. It's just, I'm curious to hear from you. What's the most snow you've ever experienced? And no lying, okay? What have you experienced in a 24-hour period? How much snowfall have you seen? And I see the numbers coming in here. It looks like D, 21 to 30 inches is winning. And I think, I mean, I've definitely seen 21 to 30 inches in a 24-hour period up here. 31 to 40 would be, I don't know, Janet or Will, have you ever experienced 31 to 40 up here in 24 hours?
Now,
Yes.
I've only been here 2 winters.
I remember a snowstorm where I think there was I think it was like 36 inches in a space of like 4 hours.
That's truly impressive. So it looks like D definitely wins, but I'm amazed. I mean, there are 7 people who say they've experienced more than 50 inches of snow in a 24-hour period, which is phenomenal. And it is indeed a very local thing, and we'll get a little bit of perspective on why that might be. You can be, as everybody who lives up here knows, you know, Chassel and areas that are, you know, sometimes called the Banana Belt. Whereas, you know, you can go up to Calumet and have a completely different amount of snow than you do here in Houghton or Hancock. So, all right. So this is a claim to fame in our house. This was after a particularly large, and obviously it didn't snow this much at one time. This was some snow, some drifting, and probably a little bit of snow pushed off the roof as well. But it's definitely, you can even see the imprint of the door here, and you know, where the door handle was stuck here. So, and one nice practical thing about this amount of snow that we get in the UP is you really save on curtains. You know, you don't need to close You don't need any kind of fashion designing or anything like that. Who needs curtains when you've got snow that basically covers your entire front window? In fact, by the spring, you feel very exposed somehow, like, oh, I'm not used to people being able to look in my windows. So. Okay, so here's the real deal. I wanted to show I know we've all seen these kinds of images, but you can look at them over and over. They're fantastic. These images are from various NOAA satellites. This one is neat because it shows all of the Great Lakes. I think you can see where we're located here. So this is Lake Superior, and the Keweenaw is almost completely immersed. If you didn't know the Keweenaw was here, if you didn't know the geography up here, you might even miss it. But we're somewhere right under one of these lake effect bands, and of course Lake Michigan and so forth. And we'll talk about some of these features. This is one of my favorites. This is just a fantastic MODIS image that shows basically a cold air outbreak from Canada, right? So the wind is coming kind of from the northwest, you can see. And you can really see nicely here, one of the terms that I'll introduce a little bit later is fetch. And fetch is the distance that the air travels over the warm lake as these lake effect snow bands develop. And you can see that right as you go off of the land and over the lake, if you were sitting here, you wouldn't see any lake effect snow. You're on the lake, but there's no lake effect. It takes some time for that to develop, for basically the convection to become deep enough and to become organized enough. And you can almost see by looking at these bands that it gets deeper and deeper and more active. And then of course it's the Keweenaw and sort of explodes. And we'll talk about why the land might have some ability to actually strengthen lake effect snow.
It's a stunning image.
It's phenomenal. It's phenomenal. This one's nice because this is just an animated GIF. So it's just the satellite image taken throughout the day, right? Every half hour or something like that. It looks like this is January 7th, 2015. And this is from, if you ever want great satellite imagery, our friends down in Madison, that's where the Space Sciences and Engineering Center is located. And they do a lot of this analysis. Okay, so I want to ask, since we're looking at satellite images, I want to ask you a question. And this is to the best of my knowledge. I mean, if somebody can prove me that there was something, before this, that's fine, but I'm pretty sure this is it. So when was the first satellite image of a lake effect snowstorm taken? What would you guess? 1964, 1971, 1978, 1985?
Oh, 1971 is winning.
71 is definitely winning.
But is it right?
I'll keep you in suspense. Okay.
I'm curious too. Raymond sent these to me earlier today, and I had a guess, but he didn't tell me the answer, so I'm waiting. Yeah,
Will emailed with his guesses, and I didn't even answer. I thought, no, I got to give him some motivation to join. Okay, so 1971 is what most of you, then 78 is a close or a second, and a close third is 1964. And before I tell you the answer, though, I have a follow-up question. So which of the Great Lakes was featured in that particular earliest or first satellite image? Can you guess? It looks like Superior and Michigan are duking it out here for first.
Well, I sure hope Superior wins this one, Ray.
You might be biasing the audience, but okay, it looks like we've got a pretty good number of results. And so Superior just edged out Michigan. So you're right about Superior. but not quite right about, oops, let's see if I can get this to go to the next slide. There we go. This is it. I mean, it's not as impressive as the modern ones, but the paper was published in 1971, but the image, believe it or not, is from March 5th, 1964. And it is lake effect cloud streets over Lake Superior. And you see that, I mean, it's fantastic. So the first ever satellite image of lake effect snow bands was actually taken, including the Keweenaw Peninsula. Right? I think you can see this. This is Keweenaw Peninsula, so Marquette's over here, right? This is the Upper Peninsula of Michigan.
All right, Ray, put the arrow right on where Houghton is.
Right, something like there, right?
Yeah, where the snow density is biggest.
I think you might be right about that, yes. And it does feel that way sometimes when you live here, you know, about in February. Okay, and then one more question for you, and then we'll get into some of the forecasting tips. It just turns out that there are places other than Earth where lake effect clouds have been observed. Can you guess which of these non-Earth bodies, some are planets, some are moons of planets that we know, right? Europa and Titan are both moons. Can you guess which of these?
Well, Europa is getting a clear advantage, followed by Titan.
Yeah, and I'm guessing that Europa is winning because, so I actually don't know as much as I should about some of these moons, but my wife is sort of Mandy knows a lot about these different planets and moons, and I think Europa is ice covered or something like that. So it makes sense.
So Raymond, it's a good thing you didn't say liquid water clouds.
I did not say liquid water clouds. That's right. And I did think about having yet another question, what were the clouds made of? But I didn't include that. So you can ask yourself just mentally. And so Titan, in fact, is the correct answer. So good job. Titan is the correct answer. And the clouds are made out of methane. So this bright spot here, and it also shows up here in a different band. These are detected by the Cassini satellite. These are lake effect clouds, which I think is really great. They're really kind of a cool thing that you can see. The physics that we're going to discuss for the next little bit is more than just water on an atmosphere full of nitrogen and oxygen. This kind of basic physics could be operating on all kinds of planets around the universe. Okay, so what are the ingredients? Now let's get down to business here. What are the ingredients of lake effect snow? So I have 6 items here, and there are a couple of rules of thumb that you can write down if you're interested in this. So the first one is a really good one. The most important thing, the most basic element that you need for lake effect snow is a strong temperature difference between the lake itself and the atmosphere above the lake. And there's a rule of thumb that I learned from my meteorologist colleagues at the National Weather Service, that the temperature of the lake minus the temperature of the 850 millibar level in the atmosphere, which is about, I think, 1.5 kilometers above the surface of the Earth. So 850 millibars is a pressure level in the atmosphere. And it's a standard, you can find standard meteorological charts for that level. And so you can download those, look at the temperature. And if that temperature difference is greater than, 13 or 15 Celsius degrees, then you're in a regime where you could potentially have strong enough convection to produce lake effect storms, lake effect snow. And it also depends on the wind speed. You can imagine if there was literally no wind, then the lake effect snow would just fall back onto the lake itself and it wouldn't be blown over the Keweenaw Peninsula. So you need wind speed. And you need a sufficiently large horizontal extent of the lake. And that's what we called before the fetch, right? So in this little diagram here, you have to have enough, it has to be a big enough lake, basically. If it's too small of a lake, it's not going to have a very big effect. And then a couple of other things that I think I can explain and will make sense. So one is friction-induced convergence. So imagine that the air is blowing along the lake, and everybody knows who's been out on the lake or even on the shore next to the lake, that the wind, it's often windier over the lake than it is over the land. And that's generally speaking because the land has more friction within the boundary layer, right? It has trees and hills and buildings and things like that. So the wind is zipping along over the lake. It hits the land where there's greater friction, and so it slows down. Well, if there's high speed here and low speed over here, you can't squeeze the air together, so it basically gets pushed up. So that frictional induced convergence causes vertical motion, and that's why sometimes the snow gets even stronger over the land than it does over the lake itself. There's another aspect of that, and that's called the orographic effect, which basically means the land is higher than the water. So when the air gets to the land, it gets pushed up. And that's part of the reason, for example, that Calumet has some of the strongest snowfalls in Houghton County, because it's one of the highest points, right?
So Raymond, you might just briefly mention why pushing up means more snow.
Oh, great. Yeah, great point. So the way you form clouds in the atmosphere, one of the most important way you form clouds in the atmosphere is by moving air vertically, moving it upwards. And that's basically because as you go higher in the atmosphere, the temperature gets lower. And so as you push air upwards in the atmosphere, it gets colder, and eventually it gets cold enough that it reaches the saturation. It reaches 100% relative humidity, and then water starts to condense out. Just the way water condenses on colder surfaces, if you in the bathroom or something, it's the coldest surfaces that water condenses out onto. So that's why friction-induced convergence or orographic effect both tend to cause positive vertical motion, and that enhances the strength of the lake effect. And then the last one that I have here, and that's the part of the same kind of thing, is you can have large scale weather systems like low pressure systems that by themselves would already produce vertical motion in clouds, and the lake actually enhances that. So you already would be getting some snow from those storms, but because of these other factors with the lake effect, it actually makes it even more snow than you otherwise would have gotten. Okay, so let's see, I'll take you to the next one. I'm going to take you through an actual example. I was kind of sketching this out the other day, and in fact, it was a week ago, Sunday, a week ago. Those of you who live in the Keweenaw probably noticed that we had a kind of a pulse of lake effect snow come across on Sunday afternoon and evening, maybe even into Monday morning. And I'm going to show you this, how I use this rule of thumb. I actually screenshotted the images that you need to be able to do this for yourself. So here's one place you can go. You can go thanks to, for example, we have colleagues at Michigan Tech, and of course at NOAA, who think a lot about the properties of the lake. And this is a map of the lake surface temperature. And you can see that it's roughly, actually, I think there's a mean value here somewhere. Where did I see it? There we go, 41.8 degrees Fahrenheit. So, roughly 5 degrees Celsius. At that time, this was November 29th, 2020, and the lake was about 5 degrees. So remember, the rule of thumb was to have about a 15-degree temperature difference. So if I go to this is my favorite website for weather. If you don't know about it, go check it out, windy.com. This one's fantastic. So one of the neat things you can do on windy.com is you can actually change the level of, you can have it show the temperature. That's what the color bar shows here. You can see the color bar on the bottom. And so this cyan color is like -10 or -12, something like that. And what I did is I actually set this windy level to 850 millibars, so about 1.5 kilometers above the surface of the Earth. And you can see that the air coming from Canada flowing down and coming over the Keweenaw Peninsula is at about, let's say, roughly -10 Celsius. So the lake was at +5. At 850 millibars is -10. There's our 15 degrees. And sure enough, if you look at their precipitation forecast, here it is. And they have this big bullseye of lake effect snow over Houghton. Turns out there's a little more to the story here. This was actually one of the cases where it was enhanced by the meteorology of the system. So there could have been a little bit of snow by itself, and the lake effect just intensified that. If you're really a weather nerd, and I don't panic if this means nothing to you, but if you're really a weather nerd, you can go download the SKU-T diagram. Right? This is like an entropy temperature coordinates diagram for the atmosphere. And you can see that there's this level. So this is 1,000 millibars, which is the surface of the Earth roughly. And there's 850 millibars. And for those of you who know how to read these charts, you can see that the system is saturated, and it indeed goes from about 0 to -10, the atmosphere, as you get to the 850 millibar level. So it really, it really does all sort of hold together to explain that little lake effect event. Maybe one of the only lake effect, really serious lake events that we've had this year. Okay, now I'm going to tell you a little, let's get into a little more of the science and talk about some of the things that we're doing here at Michigan Tech to study processes that are relevant to the weather and to pollution, to climate, to various different factors. This is the Michigan Tech Cloud Chamber Lab. This big blue box is basically a controlled environment where we can set the conditions of a miniature atmosphere according to our desires. So we can control the temperature, the pressure, the humidity. We can control what kinds of particles we put into our little controlled atmosphere. For example, we could put in soot, or we could put in salt. Different materials that you might expect would either have natural or human sources. And then we can measure all of the cloud properties that you can imagine. This gives you a little bit of an idea. Here's Will, and this is Lynn Mazzolini from the chemistry department, and Claudio Mazzolini from physics department, and Dave Ciacchetto, who might be online actually. He's since moved to Rhode Island, but and this is what the inside of the chamber looks like. So it's a big cylinder, and we do just what's happening over Lake Superior. We make the bottom of the chamber very warm and the top of the chamber very cold. And so we cause convection inside of it. And when you do that, when you have that convection and it's humid and you put small particles in, small particles like occur in the natural atmosphere into this controlled atmosphere, cloud droplets grow. And so this is like what you're seeing is a fog basically, or a cloud that's illuminated by a really bright green laser. And so each of these dots that's moving around is a cloud droplet that was formed just in almost the same way that you would form a cloud in the natural atmosphere. And the turbulence is from that, from the fact that we're heating the bottom and cooling the top. And so there's convection. So if you could go out on Lake Superior, sorry, Janet, if you could go out on Lake Superior and into one of these lake effect clouds and shine a laser through it, you would probably see something similar to this.
I was just going to say, this is so cool.
I'm glad you like it. We actually were thinking about making a cloud chamber zoom background, but that might truly be mesmerizing. Nobody would pay attention to the speaker because they'd just be listening or watching that background. Here's another one. This is kind of neat. Just the way that at the top of the lake effect storm, at maybe 1.5 or 2 kilometers, you can imagine that it's clear air above that. And one of the really complicated questions is, you know, it's turbulent at the top. It's not like in a cloud chamber where there's a rigid lid at the top. It's actually clear air. It's just very stable. But the lake effect storm can engulf that air and suck it inside of the cloud, and it changes the cloud properties. And we can study that at the Michigan Tech Cloud Chamber too. So this is another shot we've made. In this case, it's a light sheet coming up from below. And this is the top of the cloud. We put a little hole in the top of the cloud chamber, and we have a really stable interface here. And you can see the kind of mixing events as the clear air mixes with the cloudy air. And we can study how that changes the properties of the cloud. So to go to the next part, I have another question for you. So obviously to make lake effect snow or a lake effect storm, right, you need water to freeze. So if we could get that question going, this should be pretty simple, right? What temperature does water freeze at? 32 Fahrenheit, 0 Fahrenheit, minus 40 Fahrenheit, or it's complicated?
Raymond, I have to say I'm a little disappointed that you use Fahrenheit. This is an engineering university.
It is an engineering university. I happen to believe that Fahrenheit degrees have more character than Celsius degrees. Celsius degrees are just too big, you know? It's okay, so it's complicated is exactly right. It is in fact complicated. So those of you who answered 32 degrees and thought for sure you had to be right, that who would be silly enough to ask this question, it's kind of a trick. You're right that under normal circumstances, if you have enough water and if you wait long enough, it's going to freeze at 32 Fahrenheit. That's what you might call the coexistence temperature, where water and ice can coexist stably. But it's complicated because in a cloud, you have small droplets, right? So, and they may not last for very long. And so you have to think about, okay, what could possibly make those things freeze? And for this, I'm going to share a really great video that Elise made. And I'm hoping, I'm just realizing I might not have shared my sound. You guys, I might need to stop my share and restart it to make sure that I have the audio shared, because you need to hear this track. So let's just pause for a second. I'm going to share my screen again, share computer sound, and I hope it works. Okay, I'm going to press this and wave your hands at me or say something if you're not hearing the audio.
If the temperature outside drops below 0 degrees Celsius, what do you think of? Freezing. But guess what? Water doesn't always freeze when the temperature hits 0.
Okay, I'm going to pause it. Janet, can you hear this?
Yes.
Yes, fantastic.
Yes.
It could, but usually it doesn't. When it comes to researching frozen clouds and snow, it's really important to know that water stays liquid even below 0 degrees when it could be ice. That's called supercooled water. In the atmosphere, water droplets usually reach temperatures of -10 to -35 degrees below 0 before they finally turn into ice. Here's some videos I took in the physics lab. You might have seen this water bottle trick before. This water is colder than 0 degrees, but it's still liquid. For some reason, if you hit the bottle, it decides to freeze. Well, scientists don't fully know why that happens, or why this happens, or this. The same goes for cloud droplets. You have droplets in clouds that are supercooled liquid. Something happens to them, and they decide to freeze. The goal of my research project is to try to figure out the fundamental physics behind what is causing the water to freeze.
Awesome. Thanks again to Elise for that great video. And just to be clear, Elise, when she was talking about 0 degrees, she was talking about Celsius degrees. So So indeed, it's true that in a cloud, water can be super cooled, meaning that it is colder than than the temperature you would normally expect it to freeze at. So instead of a cloud droplet freezing at 0 degrees Celsius, it might freeze at -5 or -10 or -20, depending on several factors. And one of them is what kind of material is in the cloud droplet or can basically catalyze the formation of the ice.
If the temperature outside drops.
And I'm going to go to my next slide here. There we go. This is a neat experiment that we did in the cloud chamber. Let me explain to you what's going on here. So you see 4 snapshots. This one in the upper left is one extreme, and this one in the lower right is the other extreme. So what we did is made a cloud that was below 0 degrees Celsius, a cloud of droplets. And believe it or not, almost all of these little points of light that you see here. So this is the same thing. It's a thin laser light sheet sort of coming out towards you along a 2-meter path here. And it's illuminating these droplets. And almost all of these are supercooled water. So even though they're at some temperature, maybe -5 or -10 degrees Celsius, where you would normally expect them to be frozen, they haven't frozen yet. Then we start injecting small amounts of particles that we know from experience can catalyze ice formation. And in fact, they're called Snomax particles. It's a biological material that is really good at getting water to freeze at a high temperature. And if you put in a little bit of that material, you start to form some ice. And if you put more material in it, you make even more ice. And I think I told you the wrong one. This is the other extreme on the upper right. And if you put a lot of that Snomax material in it, you basically, all of the little faint cloud droplets are evaporated and you have just a few snowflakes left over. So one of the things that you need to understand to really be able to get the details of lake effect snow is how many of these particles are there that help water, supercooled water, become catalyzed to form ice. And obviously, my empirical evidence from my driveway and all of you who have lived here, there must be plenty of these particles in the atmosphere for this to be able to happen. But it turns out to be surprisingly difficult to figure out which of those particles are doing that and exactly how they're acting. So usually when we measure the amount of ice in a cloud, and then we go measure the small particles that we think would create ice, they don't match. And sometimes they're off by factors of 1,000 or tens of thousands. And so it's really hard to explain where all of that ice is coming from. So that's a mystery that we can study in the cloud chamber. And this is another process that I think is interesting and that we can study, either directly or indirectly in the cloud chamber. And that is, once you form an ice crystal or a snowflake, how does it grow? And this figure shows supersaturation. So you can think of this as relative humidity. So that would be 100%. And then here's temperature. And you see this amazing thing that there's the highest supersaturation that can be achieved in typical clouds that are mixed phase, meaning they have both ice and supercooled water coexisting, happens roughly at -15 degrees Celsius. And so this is the sweet spot for getting the puffiest, for a given amount of liquid water, what's the deepest amount of snow you can get? It's almost always a cloud that's thick enough that the ice crystal or snowflake growth took place at about -15. So that's another rule of thumb for those of you interested in forecasting. You can look at that 850 millibar level. And if it goes down into the something like -15 range, you could be in a really good spot for these, what we call dendritic growth. And you get these big puffy snowflakes. So in fact, the snow density ratio is one of the things that makes lake effect snow the most challenging to forecast, because the same amount of liquid water if you say, okay, my model tells me this amount of liquid water is going to be turned into snow and it's going to fall, that could have a density ratio of anywhere from 5 to 1 to 50 to 1. For our area, it's roughly 15 to 1, meaning one way to say it would be 1 inch, 1 inch of rain would be 15 inches of snow. But depending on where it is in this range, you could have something that's a couple inches of snow or a couple of feet of snow. It makes it extremely difficult to forecast. So I'm going to end just by putting this slide up. This is from a paper about 25 years ago, but a lot of these recommendations are still sort of similar, pretty much remaining. How can you improve lake effect forecasting? Well, you can make better models. See, all of this is based on computational models, right? And last week's Husky Bites was about some of this as well. You can improve the model resolution. You can improve the representation of the physics inside of those models. That's what we're trying to do at Michigan Tech in the Cloud Chamber Lab. You can improve the ability to map and know the detailed surfaces of Lake Superior, especially what parts of the lake are covered with ice, because that shuts off that water vapor and heat source. Improving the ability to know these liquid to snow ratios that I just mentioned. And then lastly, it would be really nice to have high resolution observational networks in the vicinity of the Great Lakes. That would be both on the lakes themselves and on the land around the lakes. So I'm going to stop there, and Janet and Will, I can take questions from you. I can take questions from the audience.
Well, thank you so much, Ray. I'm going to ask people to load up questions in the Q&A while I just make a few remarks here. And Will, maybe you can identify, Will and Ray, the first few questions to take while I kind of thank the audience and the speakers. So can you see my slides?
Yes.
Great. All right, so I just want to look back on the entire Husky Bites season and sincerely thank all of our sponsors this fall. As we mentioned earlier, you can sponsor a webinar. I do want to assure you, we're going to hold the webinar whether or not we have a sponsor, but it's an opportunity to give in support of your department or in support of student scholarships. And so if you would like to do that, I encourage you to do so. All you need to do is send an email to engineering@mtu.edu. And while I'm here, I want to really sincerely thank, we have a Husky Bites team. So Kim Geiger, who writes and posts the blog and social media. Thank you so much, Kim. Sue Hill, who is the name behind Husky Bites, who is running the show. And Danielle Davis. I just want to sincerely thank all of you. Danielle Davis is engineering@mtu.edu. So when you write there, Danielle is writing back. So I want to thank the team for all their work and support of helping us learn while we're enjoying our evening. Thank you again, Michael and Karen Gregory. I want to point out that they have done a challenge grant to us. They are going to match dollar for dollar up to $25,000 of gifts to the Michigan Tech Annual Scholarship Fund. And so how to do that, you might want to take a screenshot of this, or you can send an email to engineering@mtu.edu, and Danielle will let you know how to do this. But the directions are kind of shown there. I also want to point out that our spring season, and I'm using the word spring in quotations because it's going to be January, but the sort of spring semester season of Husky Bites will start January 25th. And so the last thing I want to point out are that at Michigan Tech, there is a whole suite of online graduate certificates. And I'm only going to mention a few that were recently approved that are offered through the College of Engineering, but I want to assure everyone there are many more than these. So what is a certificate? You can think of it as 1/3 of a master's degree. It's a set of 3 classes that taken together lead to a credential that shows up as something on your transcript, you can actually stack 3 of them to create, to accumulate toward a master's degree if you should choose to, or to contribute toward a PhD. So here's the names of some of them. I encourage you to watch the website, because we're going to be posting a new web link that describes all these very soon. This is the second set of them. They're all in the approval process, kind of working their way through the university approval system. So if you're interested in learning more, send an email to Danielle by sending an email to engineering@mtu.edu. We'd love to hear from you. Next season starts off January 25th, and I'm going to stop sharing screen now. Well, if I showed this 3 weeks ago, I believe, but I do want to just have a strong acknowledgement to all the people who have given just generally in support of our Huskies. There's been over 300 donors who gave to the Husky Emergency Assistance Fund. There have been more than nearly 200 donors to the Admission Tech Annual Scholarship Fund. There's an emergency fund that has been supported. And so overall, over $150,000 has been raised. And so I just warmly and thankfully acknowledge all of the support that has been received. All right, and I'm turning it over to Will and Ray to start answering questions. And I think we have quite a few questions, 41 open questions. So I'm going to leave it up to you guys to pick the questions.
So Raymond, maybe we'll start with an easy one, which both of us can address. Your favorite thing about Fairbanks, and how does it compare to the Keweenaw? And I'll start that one. My favorite thing about Fairbanks was the people that I met and knew there. But in terms of the environment itself, there is very little to compare to going outside. I saw Comet Hyakutake from my outhouse, and there's a story behind that, but I will leave that for another day. I saw Comet Hyakutake through the Northern Lights. I will never forget that. How does it compare to the Keweenaw? It snows a lot more here. I never had to shovel my roof in Fairbanks.
Yeah, I agree. I mean, Fairbanks is kind of like the Keweenaw. I remember when I moved here, I moved from Boulder, Colorado, and there was somebody who worked at NCAR there who lived in this area, and she said, the climate's cold, but the people are warm, and that's always been true. And that's true of Fairbanks too. Just friendly, good, nice people, and it makes it a really pleasant place to live. So I saw one that I thought was interesting. Well, a few comments about some of the snow records that people have seen, which are really amazing. The one from Japan that is incredible, and I think Matt Zika had one about a nor'easter. And he said, maybe my question could have been confined more to just lake effect snow, but it's fair enough. So obviously in some mountainous regions, you can get truly massive amounts of snow in short amount of time. I also see one here about can a radiosonde be called a satellite? And I would say probably, when I said satellite, I meant, orbiting the Earth, let's say. So radiosondes are super important for atmospheric observations, so basically weather balloons. But I wouldn't call it a satellite, I guess.
So Raymond, here's another one, and I think you touched on this in the presentation when you talked about the satellite images, but maybe we could just clarify a little bit. Is lake effect snow significantly heavier to the east side of bodies of water?
Yeah, good question. I think the gears are turning here. I think that's usually true for the Great Lakes, because often in the winter, the wind is coming from the west or northwest. But it doesn't have to be that way, right? You can have, one of the nice things about the Keweenaw is you can have wind from the west, north, or east, and you can have equal opportunity for lake effect from all of those directions. So I think in practice, yes, at least for the Great Lakes, but I'm sure you can come up with exceptions to that.
All right, I'm gonna read one out that's just funny. So Austin says, "Good job, Raymond. You aren't nearly as boring as your son says you are."
Oh, that I think I know which Austin that is. Yeah, another Michigan Tech alum troublemaker. Um,
Yeah. And
yeah,
then a second one, this is from Richard. I attended Michigan Tech 1967 to 1971. So this is Richard Sackney. I recall flurries falling from clear blue skies in January and February at temperatures of 10 F and less. What is the physics that supports those events?
good question. I mean, there is a phenomenon known as diamond dust, but that's more like that's more of a Fairbanks phenomenon, where you can literally have homogeneous nucleation of ice from essentially fog droplets. But I don't think that would be what was observed here. My guess is it's either lake effect snow that has blown out of, I think most people who have lived here have experienced the cyclic nature of lake effect snow. It'll snow like crazy for 20 minutes, and then it can actually get almost blue sky, and then it'll start snowing again for 20 minutes, and it'll just go back and forth. And that's those bands being blown over you, right? Those lake effect snow bands that we saw in the satellite images. So if you're outside of one of those bands, it's really possible that you could have at least a little bit of snow blowing in. And then there's also just blowing snow from the ground. If it's windy, you can get snow blowing from the ground that looks kind of like snowflakes.
All right, so we have a big record this is from John Stockering, who says that he experienced 7.5 feet on Mount Ibuki, Japan in 1927.
I saw
John,
that.
you weren't alive in 1927, were you? No.
So Raymond, this is a question from a physics alum, and I know it's something that you've thought about, so I'll just relay the question. So is your work on ice nucleation beneficial to improving safety on aircraft? I've flown through clouds, and sometimes you get ice and sometimes you don't. It's very unpredictable. What should I look for if I want to skip work and score some awesome powder at Mount Bohemia?
Yeah, a couple of questions there. So on the aircraft icing, I would say yes, there are some links. I mean, we aren't specifically studying aircraft icing per se, but if you understand ice nucleation, then you're understanding an important part of aircraft icing, because the conditions that you need for aircraft icing are not very many ice nuclei in the atmosphere, so that you have supercooled water, hasn't been catalyzed to freeze yet, and instead the catalyst is the wing of your airplane. And all you need are a few millimeters of ice on a wing to change its shape enough and change the drag and the weight, and it can be catastrophic, of course. There are some really interesting studies going on a phenomenon called ice phobic surfaces. And I think there are some people at Michigan Tech working on related topics, and other universities as well. If you could make not just for wings of aircraft, so think about turbine blades for power generation, or all kinds of, even the windshield of your car. There are all kinds of practical applications that if you could make a surface that would either not let water freeze on it in the first place, or allow frozen water to shed off easily, that would be an extremely important improvement.
So there's a point that a couple of people have made in the questions. So I'm looking in particular at one made by Paul Jones. If there are insufficient nucleation sites, it would seem water would stay liquid, and then references molten metal supercooling of cast irons, as Dr. Runman or Dr. Mikkola once explained in MY 101 or the metal castings class. So obviously this nucleation phenomenon has implications far outside of atmospheric science. And actually there's also a point here in the Q&A raised by one of the folks in Nagani, saying that, yeah, there was a freezing drizzle event in northern Wisconsin not too long ago, simply because there weren't enough ice nuclei in the atmosphere to freeze them. But yes, if there aren't any nucleation sites, then it will stay liquid, and you get freezing rain instead of snow.
Yeah, it's definitely true. In fact, just the other day, Elise and Will and I we were having a research meeting, and we were looking at some papers essentially from the metallurgical literature, trying to understand some of what they've discovered about nucleation. So these principles of nucleation pop up all over the place.
Well, and there's a question from David Shonard. How common are cloud chambers at other universities or national labs?
Yeah,
and
it's a great question. And oh yeah, and what is unique about MTU's chamber, right?
Right.
So they're not common. I think, so as far as we know, our cloud chamber is the only operating cloud chamber in North America. There are a couple of chambers in Europe, and China has built a huge chamber in Beijing that is really impressive. The Michigan Tech Chamber is unique. The way that we create clouds through this convection method that I explained before, where we heat the bottom and we cool the top, is, I believe, the only one like it in the world. So we, at least for now, we have a corner on that market.
So this is one isn't quite so much of the atmosphere, but I think it's interesting just because I've noticed it myself. Why does snow squeak when you walk on it?
You got that one, Will. I don't know.
So this is a guess, but I think it has to do with the moisture content. If you go outside and you walk through snow and it's right at the freezing point, so if it's 31 degrees Fahrenheit, then the snow is not going to squeak. But if you go outside at -10, the snow is very likely to squeak. In fact, I noticed snow squeaking much more when I lived in Fairbanks than I do here. And I think it has to do with the moisture content and how the grains are rubbing against each other, and whether there's a little bit of liquid to basically make them slip past each other more easily. That's my guess. There are other folks who know more about this than I do, but I think that's at least where I would start.
Well, and there's lots of questions about nucleation, and it is a fascinating subject, but this question's from Mel Visser. Does each snowflake require a particle to induce nucleation? Or is it a catalytic type chain nucleation?
Question. Yeah, catalytic change. So I would say, in the simplest understanding of things, yes. So you need a catalyst for every snowflake you get. But there definitely are processes that are known to occur under certain conditions in the atmosphere. They're called secondary ice formation processes. And you can produce, once you get an ice crystal, you can sort of get a runaway effect and a cascade where, one ice particle that's growing can produce more ice particles. And that's sort of a big area of study right now. I see from Margaret, can you freeze the moisture in the cloud chamber to create snow? And yeah, definitely, we can do that. And in fact, we try to study exactly these kinds of processes. Like, do you get one snowflake for every nucleus particle that you put in the chamber, or can you get multiplication effects going on?
And to follow up on that, there's a question here about thunder snow in our cloud chamber. And this is a question that we get quite frequently. So can you make lightning in your chamber, and can you make a tornado? And the answer is no, we cannot make a tornado. We probably could make lightning, but we're not going to. But because we have sensitive equipment and large amounts of electricity leaping from one point to another just makes us justifiably nervous. And you would need lightning to get thunder, so no thunder snow.
Well, and Ray, I want to point out a comment from Chi Sheng Fong. So this is, hi, Dr. Shaw, this is Chi Shang. Very nice talk. I worked in your lab around 2004-05.
Of course,
So,
Shishing, nice to hear from you.
And then a question from Jennifer Slack. Why does lake effect snow take the form of bands, or have we answered this already?
We have not answered it. So when you have convection, let's see, I might even have a little slide I could share on that, but when you have convection, you basically create regions with updrafts and create regions with downdrafts, and they can become organized. And when the wind blows in a certain direction with a certain speed, that organization turns into bands. I know that's not a very satisfactory answer, but let me just, I guess I need to share my screen to show this, huh? So this is a famous picture of Rayleigh convection. And this is not in the atmosphere. This is just a thin layer of fluid in the laboratory where they're heating the bottom. This is looking from above, and here's a close-up. And you can see that you get these little cells where, you know, with, as you can see from the diagram over here, with the liquid going down on the outside and coming up on the inside. And so it makes these little hexagonal cells. And the same type of thing. So you get this organization of the convection. And if you have, you know, different types of heating, different types of fluids, it can actually become really exotic. And these are pictures of all the different cellular flow patterns you can get. And this is just in simple, relatively simple liquids. And once you have wind, like I said, it takes these closed cells and actually stretches them out into bands. So great question, big area of research.
All right, and so we have a prospective student who would like to know what the best trails for fat tire biking are, and how long should they wait for them to be usable. So if either of you has the answers to that question, go ahead and state it, but I encourage any of the participants who might have the answer, just write the answer in the Q&A. Ray, are you a biker?
I'm a biker, and last season was my first season with a fat tire bike. I'm completely addicted. I've skied, you know, for years, but that's like a whole new way of experiencing the snow. So I highly recommend it. And the trails, there's trails up Swedetown by Calumet, and really great trails on Churning Rapids in Hancock. Highly recommended. Definitely a reason to come to Michigan Tech.
And Raymond, how much snow do you need before you really start enjoying fat tire biking?
Well, I've been riding now. I mean, you don't need the fat tire bike for current conditions because there's just, you know, whatever, a couple of inches of snow on the ground, but it's kind of fun. Once you get, you know, more than 6 inches or so, then you'd be hard pressed to ride a regular bike on that. And it is nice that, you know, for the 2 trail systems that I just mentioned, they groom the trails specifically for fat tire bikes. And so it makes it really nice conditions.
My husband just got one this season, and so he's been enjoying it a few times already. So we're on the hour. I always take this opportunity at 7 o'clock to thank everyone for being here, and to thank both of the speakers, both co-host Dr. Cantrell, Dean of the Graduate College, and Physics Professor Ray Shaw. Thank you so much for your time. This was a fascinating talk, Ray. I've learned so much. We are going to continue to take questions. You know, I've been trying to write which ones are answered, but we still have 42 open questions. So when we answer a question, just write down answered live. But are you guys willing to hang out with this many unanswered questions? Are you okay to 7:30?
You bet.
It's kind of a late night. So audience, thank you for joining us. If you need to go have dinner, please go ahead. But we're gonna, with this many unanswered questions, I think we should just keep answering them. So Will.
There's so this is a question that's near and dear to my heart right now, because I've been thinking about lots of pieces connected to it. Is basically, when salt water freezes, how does it squeeze the salt out so that the ice is actually fresh water. It's not salty anymore. So the brief answer is, and this gives me a chance to use my water molecule. So this is a water molecule. This is a hydrogen, and this is a hydrogen, and there's the oxygen right there. And the way that water forms a bond with another water molecule is something like this. So it points in a specific way to the other water molecules, and then they lock together to form the ice lattice. Water doesn't like ions getting in the way of its lattice. And so it won't form those bonds as easily if there's an ion in the way. And when the ion jiggles itself out of the way, now you can form a bond. So essentially the water will not form those bonds if there's an ion, which is the salt, in the way. So the ions get pushed to the interface until you get a really concentrated brine solution that won't freeze anymore. And it's basically one ion at a time that the ice, the freezing front, the way the water freezes, pushes those ions out one at a time. And that's what gives you fresh water instead of salty water when you freeze it.
So I see one from Adam here. I don't know if Adam's in the UK, so he might not be on anymore, but he says, would you be able to replicate and analyze an aircraft contrails environment? I assume he's referring to in the pi chamber, in the cloud chamber. And yeah, good question. I mean, in some ways, the way that the cloud chamber operates is very, very much similar to the way an aircraft contrail forms, basically mixing between warm, humid air and cold, humid air. So yeah, I would say we could probably replicate those kinds of, we certainly can reach those temperatures.
Well, and this question's from an alumnus who grew up here, and the question is, do you have any thoughts about climate change effects on CC snowfall trends? And I don't know what CC stands for.
I'm guessing copper country.
There we go. Thank you.
I'm guessing. Yeah, that's the question that everybody wants to know the answer to, but Pengfei last week sort of touched on this. And I mean, I would say anybody who's willing to answer that question with confidence, I wouldn't believe them. So maybe I should not say it quite so bluntly, but it's, there are so many delicate things involved. So climate change itself, of course, we can have confidence, but in this case, how will lake effect snow respond to climate change is a really tricky thing because, the frequency of cold air outbreaks may be higher than it has been in the past. Lake levels are changing. Lake temperatures maybe are slowly creeping up. So, I mean, let's just take a scenario. If we have enough cold air outbreaks, and if the lakes are actually getting warmer, then, you could guess that, well, maybe there's going to be more lake effect snow. Maybe maybe the winters will be a little bit warmer, but they'll be even snowier. On the other hand, if there are so many cold air outbreaks that we basically freeze over the lakes more frequently than we have in the past, then we might end up with less lake effect snow. There are so many factors intertwined on that one. It's exceedingly difficult. Making a prediction of temperature is a much easier thing to do than a prediction of precipitation, first of all. And then making a prediction of snow precipitation is even more difficult. So great question though.
So Raymond, here's a question from someone named Ben Shaw.
Oh boy.
I think you might recognize that name.
Yeah, depending on the question, I might.
Is it possible to have lightning or thunder present in snowy conditions during the winter?
So I think the answer to that is yes. I mean, you mentioned the thunder snow before. So I can't say that I've ever observed it. I don't know. Have either of you ever observed lightning in the winter or thunder snow?
I've heard thunder.
Yeah, apparently it's a thing. So I don't know much about it, and I don't know exactly what conditions would cause it. but I definitely have heard that it exists.
So on a related question, Chris Anton, is the generation of hail significantly different than the traditional snow?
Could you repeat it? By the way, hi to Chris. Chris is another MTU alum who is at Oak Ridge National Lab now.
Is the generation of hail significantly different than the generation of snow?
Yeah. Hail, generally speaking, hail requires cycling. So you know, maybe you start with some snow and then it collects supercooled water and grows to a certain size and then gets cycled back up into the top of the storm and falls through again, and that may happen multiple times. And in fact, the people who study hail will actually they'll slice it and take thin sections, and you can see the layers, just like they look like tree rings. You can see the layers of the cold growth and the wet growth as it cycles through the storm. They're really interesting. So hail is another thing that's actually quite complicated to forecast and understand in detail.
Well, and we have a question from Darwin, which goes as follows. If the temperature at 850 millibars is so critical to lake effect snow prediction, is there a non-balloon laser method to measure temperatures at altitude?
Oh, good question. There are laser methods. So there are several groups around the world who use Raman spectroscopy for a certain kind of light scattering, and you can basically determine the temperature of a gas using LiDAR. So I mean, these days everybody's pretty familiar with LiDAR because of automotive LiDAR, right? So it's basically a laser that's shot out at something, and then you measure the reflected or the scattered return, but you do it in range gates, kind of the way you do with radar. So by measuring the time for the pulse to go out, bounce off of something and come back, you know the distance. So you can do that. You can shine a really intense laser up in the atmosphere and measure the time of the backscattered light, and in this case, the Raman scattered light, and you can say something about the temperature. I think that's a pretty complicated measurement to make, so I don't think it's widely available.
So Liz Carr asks, can an ocean cause lake effect snow? So can you get ocean effect snow?
Absolutely. Most definitely. Same principles apply. I mean, except it's salty, so that changes the bottom boundary condition a little bit. The exact humidity at the water is slightly different because of the salt, but the same kind of idea you can have. So for example, if I've been on the west side of the main island of Japan, and those guys, it's sort of like the Houghton of Japan, the place that I visit. I mean, they get these unbelievable snowfalls, and it's, what is that? The Sea of Japan, I think. That's maybe the water comes, or the air comes off of whatever, Siberia, I guess, and blows over that sea and then hits Japan. And there's the same kinds of things: the orographic lifting, the friction induced convergence. All of those factors come into play.
Yeah, I was just looking. One of the first points in the chat, in answer to where did you experience your record snowfalls, John Checken says the 31 to 40 inches was in Seward, Alaska, which is basically ocean effect snow. And I recall watching the news in Fairbanks, and they would talk about Valdez, sometimes the pass just north of Valdez getting feet of snow within hours when they would close the road. And it was because there were air that's coming off of the warm ocean, and it's cold, and it hits land, it slows down, and then it's forced up over the Alaska range.
Well, so here's a question from Anna. Can you explain the banana belt, and where is it, and what is it?
Oh, okay. Yeah. Well, in the context that I used the term, I think banana belt can probably have multiple meanings, but here locally, some people maybe somewhat in jest refer to certain areas as the banana belt. Um, and yeah, I mean, nobody's growing bananas there as far as I know. That might be an exaggeration, but there are areas up here that are relatively sheltered. They're, relatively warm and snow free compared to others. So they tend to be regions, so like on the Keweenaw, regions on the eastern side of the Keweenaw Peninsula tend to be a little more, you can imagine the air is forced up over the Keweenaw and then it goes down. And so the parts that are on the down eastern side, like Barica and maybe even Chassel, tend to have
Okay.
less.
No, somebody should have told me that before I bought a house here in Houghton.
So there was another question about what place on Lake Superior gets the most lake effect snow?
Ooh, good question. And I would defer to Matt on that. I don't know if Matt is still on the call. You could just post it in the Q&A. I would not want to hazard a guess. I mean, it must vary a lot. I'm sure the Keweenaw is in contention for for that award, but
Is this Matt Kalfer?
Matt Zika
No,
from
I don't
National
see
Weather
him.
Service.
I don't
So,
see him. I don't
I
see him
think-
still on.
I think Munising also has a claim to fame there.
could be actually.
They get a lot of snow.
All right, so this is a fun question from Margaret. Have you been able to make snow in the cloud chamber?
Yes.
Ha ha ha.
So, well, I mean, let's say ice, frozen water. It's, part of what makes snow is the fact that it grows in those beautiful shapes, right? Those ice crystals that are hexagons or dendrites and things like that. But to grow those things, they have to be able to fall for a long time under conditions where they can be progressively getting bigger and bigger. And in the cloud chamber, the most things can fall through is about 1 meter. So the particles never get very big. So you don't get any beautiful, fluffy snowflakes out of the cloud, at least not yet. We'd need a much bigger cloud chamber for that.
So as I predicted, Ray, people want to know how they get a Blizzard Zoom background like you have. And while you're answering that, I want to show, I got to turn this right side up though. So to our loyal Michigan Tech, or to our, people who've been following Husky Bites webinars, we're going to be sending a flag to you that is two-sided that you can display in the background of your Zoom office or outside in your garden or wherever you wish. And so Danielle will likely be emailing you. And if you would like one, you should let her know. And if you have a prospective student that you think should have one, you should also let her know that. And so I know we have a few minutes left. I also wanted to say happy holidays to everyone while we're thinking of snow. I wish everybody a safe, and snowy holiday, I guess. We haven't had enough snow here. What's been going on, Ray?
Yeah, well, that tells you something about how complicated it is. Matt Zika from the Weather Service emailed me today and said, we still got a lot of December to go, but this would be truly a record-breaking year if we ended up with November and December with less snow than we had in October. It is very strange, but I let's just say I wouldn't put my money on it. I think we'll get plenty of snow before Christmas. But yeah, somebody had a comment in here about taking grandkids dog sledding south of Marquette in the UP December 17 and 18. Are we going to have snow? Yeah, sorry. It's forecasting that far out is like trying to predict the stock market that far out.
So Janet, there's a comment here from Jim Bench, and I want to mention a couple of things about that. So Jim is an alumnus of Michigan Tech. He graduated in 2003, I think, from mechanical engineering. Jim is also the lead engineer at Russell's Technical Products, the folks who built the cloud chamber. And so he's in attendance and mentioned that there are quite a few people from Russell's also attending. And the question, Raymond, is, and specifically says, we're proud to be a part of this. So the question is, in your opinion, what is one of the most impactful studies that you've done in the cloud chamber?
Yeah, good question. First of all, hi to Jim and everybody at Russell's. Those guys are fantastic. The people at Russell's are really, really amazing. And, you know, the fact that it worked out so that this contract, when we built the cloud chamber, could go to Michigan Tech alum. It wasn't a given, obviously. It's a bidded process and has to be all by the books and everything, but it was really great to be able to work with them, and they did a fantastic job, and we continue to work with them. They're down in Holland, Michigan. So the question about most impactful study, that's a good one. I would have to say that we've gotten quite a bit of attention for a study that we did about 4 years ago, where we looked at basically if you grow, if you make a cloud in still air, or if you make it in really turbulent air, how do the properties of the cloud change? And especially, what if you do that under polluted conditions or clean conditions? And it's a really interesting study. It turns out that we as humans, we change our environment in a lot of ways. And one of the ways is we're really good at generating aerosols, small particles. I don't mean COVID-19 aerosols. I mean, combustion byproducts and things like that. So when we make these aerosols, we actually change properties of clouds. And we can study that in the cloud chamber. We can make the same cloud, thermodynamically speaking, it's the same cloud, same amount of water, but we can make it under pristine, Pacific Ocean kinds of conditions, or we can make it under, mega polluted city conditions. And you'd be amazed. You can see it with your eye. You don't need any measurements other than shining a light in the chamber. You can totally see a huge difference in the polluted clouds from the non-polluted clouds. It's pretty neat stuff.
So there's a question in here about measuring the air temperature and wind speed on the lake. And this actually dovetails quite nicely with the seminar from last week. Do they use buoys, or is it all satellite imagery? And so I'm going out on a limb here. This is not my area of expertise. I know there are buoys out on the lake. I don't recall if they leave them there all winter. But I will defer to people who know more about that. So there are buoys out there that they use, and there's also techniques to get some of those quantities using satellite imagery, although I don't know if they use it over the lake. That might only be over the ocean. But that's actually one of the gaps that we have, is we don't have a lot of data from out over the lake. That's one of the reasons why forecasting here can be a little bit tricky, is you can't just look a few miles upstream and say, well, it's doing that there, so it's going to be doing that here in 30 minutes.
Well, and this is a comment from Chris Occhipinti. I'm pronouncing it Italian here. So the comment is, hi guys, still doing atmospheric science professionally after all these years. You did a great job making this a fascinating subject. Class of 2004, applied physics.
Mm-hmm. Awesome. And another alum, Peter Kiefer, who also worked in my lab for a while, and I think probably had both Will and me as in various courses. He asks a really good question. How well is the low-level understanding and modeling of cloud formation on the small scale, like in our cloud chamber? How does that translate and inform our understanding of the large-scale structure of lake effect snowbands? So I mean, large scale structure of atmospheric cloud processes in general, it's, you know, we hope that there's this trickle effect, right? That the more you learn about the details, the better you're going to get at representing things in the sort of really coarse resolution models like weather models. Cloud bands in general, or specifically, I would say maybe not a whole lot, because that's I think you need more of a large scale dynamics environment for that. But yeah, we hope that, I mean, that's one of the reasons we do research is, you know, we're hoping that bit by bit, we chip away at it and, you know, make the world a little bit better, answer some important questions, and understand the atmosphere a little more thoroughly.
Well, and we're getting on close to the half past the hour, which, and I know I promised each of you we would end at 7:15, and I of course I didn't tell the truth there, but maybe Will, you could pick another question to answer, and then Ray, maybe you could make some closing remarks to wind up the evening. And my closing remarks, I just want to thank you again and thank the audience and wish everybody a happy holidays.
Well, this one kind of scrolled past, but I got to come back to it. And Raymond, I think both of us have been here long enough to at least mostly get the reference. What role does Hiki Lunda play in the production of lake effect snow?
I did see that one. Good question. And I don't know, I can't answer that, but there do seem to be things going on in lake effect snow that are really hard to predict. So one never knows. There could be some Finnish magic going on out there that I'm just not sure about yet.
Is there, I mean, what do I not know about that phrase?
Will, I'll let you explain. I don't think I can really do it justice. Find somebody that you know who has lived in the copper country all their life, and ask them about Hiki Lunda. It really wouldn't be appropriate for me, an outsider, to try to explain this.
Fair enough. Well, Ray, do you want to close us out?
Sure. I mean, just once again, thanks, Janet, and to the College of Engineering and Michigan Tech for hosting these things. I think they've been really great. It's a great way to reach out to people and have people remember good times at Michigan Tech and remember the snow in this particular case. Interacting with the alumni and just friends of Michigan Tech in general, I think, is one of the highlights of the job. I don't know, when you take a job as a young professor, you don't necessarily think about those things because there's so many other things on your mind, but really interacting with so many people who have come through and just seeing their careers and their lives develop is really kind of a highlight of the job. And so it's great to have seen so many familiar names and to hear from people who are interested in this area and our unique weather. So thanks a lot for tuning in.
Well, and thank you, everyone. And thank you again to the people behind the scenes. Good evening and happy holidays.
Bye-bye, everybody.
Thank you. Good night.